welcome to Electrical Circuit Analysis Lecture 2. In the previous lecture 1, we discussed about the introduction to the course Electrical Circuit Analysis, how this course is relevant for the electrical science study and how it is applicable in various system analysis, and also we have seen the sources, various sources, voltage source, current source, dependent and independent sources. So, in this lecture we will be discussing about the source transformation of ideal, we will be discussing about ideal sources and practical sources, source transformation and source shifting. Okay. So, first let us look into the different types of sources that are ideal sources and practical sources. Ideal sources are those which do not possess any kind of internal resistance or internal impedance. So, the sources with zero internal impedance are known as ideal sources. So, these sources will be characterized by their source value, either the current or voltage. If the source is a voltage source, it is characterized by voltage source. If the source is current source, it is characterized by current source. The values of these sources will remain the same for infinite amount of time. Okay, that we are calling it as sources. A source is that which will be delivering a positive average power, that we have discussed in the previous class. A source is one that will deliver the positive average power. So, the voltage source will be having the voltage value across its terminals for infinite time. So, here infinite time mean a long time or the time duration for the entire operation of a system. Here infinite time does not actually mean the infinity. Here the infinite is used, the term infinite is used to define the operating time of any system. Okay, so, as long as the system is under operation, if the source is delivering the same amount of voltage, then we call it as a ideal source, okay, or generally a source. And these ideal sources, these do not possess, do not have internal resistance or internal impedance. These do not have internal impedance. Okay. Then what are practical sources? So, practical sources which we find in practice. Okay. So, these practical sources have finite internal impedance. These have finite internal impedance. Okay. So, we already have seen how the sources are represented. Let us consider independent sources first. So, the ideal source are given as, so this represents a ideal independent voltage source of E volts with the source value of E volts. This represents a ideal current source of value I amperes. Okay. So, this E volts will remain constant across this terminal for infinite amount of time. Then this current I is delivered to this external circuit connected to the terminals for infinite amount of time. Hence, these are known as the sources. Okay. So, the other sources are practical sources. Let us see. So, how a practical voltage source and how the practical current source are represented. So, let us take first the voltage source. Okay. So, the practical voltage source is represented as, first we represent or we take the ideal form of representation E, and to this E there is a small series resistance or impedance connected. So, this is how a ideal voltage source is represented, and across these terminals we will be connecting. So, this is the load RL. So, this part will form the source, this is source, this is load part. So, this internal resistance R is inclusive in the source. Okay. This R is not a series externally connected resistor, it is a internal resistance of the voltage source of E volts. Okay. So, this is how we represent the voltage source practically. Now, if I consider the voltage of the voltage source and the voltage across the load, let the voltage across load be VL. Now, when RL is connected to the source, a current I flows. Let me take this as a current IL, the load current IL. Now, IL can be given as E divided by R plus RL, okay, E divided by R plus RL, and the voltage across load VL, is given by IL into RL, and this voltage VL is not equal to the source voltage E. This voltage VL is not equal to the source voltage V, okay, because there exists a small amount of voltage drop across this R. There exists a small amount of voltage drop across this R. Now, if I write a KVL equation for this loop, my VL will be equals to E minus IL into R. So, the terminal voltage of a practical voltage source is not the source value of the voltage source. A small amount of voltage drop internally will occur across its impedance, its own impedance, and the terminal voltage available is smaller than the actual source voltage of the voltage source. So, this is the difference between ideal source and a practical source. Whereas, in ideal source, if we consider, okay, whether I connect any load here, okay, suppose if I connect a load RL and it will also circulate a current IL, my IL is given by E divided by RL, and the terminal voltage VL, okay, is equals to E. Okay. So, this is the difference between the ideal voltage source and a practical voltage source connected in a circuit. So, ideal voltage source will be providing the same amount of source value to the load, whereas the practical voltage source will be providing the terminal voltage lesser than the source value by the amount of drop across the series impedance or series resistance. Okay. Now, how do I represent the ideal current source? Okay. So, basically the current source is realized using voltage source. In practice, it is difficult to realize current source alone. The current sources whatever we get, those current sources are basically realized from the voltage source. The connections will be made in the system in such a way that from a particular node or from a particular branch a constant current is obtained, okay, and that branch is considered as current source. But when we see practically, the availability of current source is very rare. Okay. So, how to get a practical current source, or sorry, before that let us see the VI characteristic of a voltage source. Now, if I plot the terminal voltage, against the load current, let this be VL, then in an ideal case we observe here, irrespective of the terminal load connected, my terminal voltage will remain equals to the source voltage E. Okay. So, in the characteristic, okay, we can write here, I can mention this as the terminal voltage E. Okay. So, this is my E, the same source value that the voltage source possess. Now, if I plot the VI curve or VI characteristic for an ideal voltage source, where there is voltage drop I into R existing, in series, then the terminal voltage will be slightly decreasing from the no load terminal voltage. Okay. So, the no load terminal voltage is E in ideal case, whereas in practical case there is a slight drop in the terminal voltage value equals to IL into R. So, as the load current increases, the drop also increases. So, as the load current increases, the deviation from the ideal curve is more, and this gap is the voltage drop, series voltage drop across the internal impedance of the source itself. Okay. So, this is the VI characteristic for a ideal for a practical voltage source and ideal voltage source. For ideal voltage source, E will remain constant irrespective of the current. Okay. So, next when we see the practical current source. So, practical current source, like I told, can be realized using the practical voltage source, practical current source. Now, let us consider a source of E volts having a internal resistance of say Ri connected through a switch to the load. Let A and B be the load terminals. So, let this be switch S. Now, when switch S is open, my IL is 0 or I is 0. Let this be the current I. My I is 0. Okay. Now, when switch S is closed, my I will be is equals to E upon Ri plus RL. E upon Ri plus RL. Okay. Now, this I will rewrite this current I in such a way. Now, I will multiply and divide the RHS of this current equation by the internal resistance. So, let it be E by Ri into E divided by Ri plus RL into Ri. So, I will multiply and divide the RHS of current equation by internal resistance Ri, and I will rearrange the terms such that E by Ri into Ri divided by Ri plus RL, okay, Ri into RL. So, there are two terms in the RHS of this equation. So, when I observe the first term, okay, when I observe this first term, the numerator and denominator are the constants of the source, where E is the source value, where Ri is the source impedance, and once the source is designed, developed and put it into the service, my source value and source resistance will remain constant. Therefore, this ratio yields us the constant current in the circuit. So, I will replace this ratio with constant current, and this constant current I will consider it to be a short circuit current. I will take this as ISC into the ratio Ri upon Ri plus RL. Now, what this ISC means is, it is a short circuit current of the source when the load terminals are shorted. So, if I take only the source discarding the load, now if I take only the source with internal resistance and the switch S is closed and the load terminals are shorted, this is Ri. So, when the load terminals are shorted and the switch S is closed, there circulates a current under short circuit condition of the load terminals, and this I call it as short circuit current. Now, this ISC is equals to what? It is equals to E over Ri. So, I can realize this ratio of E to Ri to be a short circuit current. Now, what happens with this? And if you observe this formula or this expression of current I, this reminds us the current divider equation. That is a current divider equation where there are two resistors connected in parallel, one is Ri, other is RL, and this ISC forms the main current entering the parallel branches. If I want to realize this expression in the circuit form, I can write as Ri, RL, and this is where the ISC is entering the parallel branch, and this is the current I. If we observe this expression, okay, if you observe this expression, this is a current divider equation, okay, which will give us this circuit. Okay. Now, what is this ISC? This ISC is a constant current, which is the ratio of E to Ri. So, a constant current entering the parallel branch. So, a constant current wherever I am getting, I can visualize that constant current as a current source. So, instead of keeping these terminals open, what I will do now is, I will be representing the left side of this load as a current source. Now, equivalently what I will do now is, I will take a source, help of a source, this is my RL, this is the current I. Now, I will, the source value I will assign to this current source to be ISC, and this is the resistance Ri. Now, if I want to visualize this circuit with a source and a load, the part of the circuit left of the load forms source and this forms load. So, I can represent a current source, a practical current source with a ideal source, current source of source value, a constant source value, and a internal resistance in parallel to that. So, if I want to represent a practical current source, it would be like this. And these terminals A and B. So, from where did I get this? I got it from the practical voltage source. So, a practical voltage source can be represented as a practical current source, and this is called source transformation. So, here I can write a practical voltage source, having the source value E, internal resistance Ri, the load terminals A and B. It can be equivalently represented as current source with a source value of let me take this as I, okay, with a source value of I, keeping the internal resistance of voltage source in parallel to the source of I amperes, such that my current I is equals to the ratio of voltage source value to the internal impedance of the voltage. So, this is the source transformation of voltage source into current source, and vice versa can also be done. I can also represent voltage source from the current source. Now, if I have a current source representation in the circuit, I can equivalently represent it by voltage source by taking E is equals to I into R and keeping this resistance Ri in series to the voltage source. So, I can transform voltage source into current source and current source into voltage source. So, this is called source transformation. Now, if I observe the characteristic of current source, EI characteristic of current source. At any voltage, my current is remaining constant. At any voltage, my current is remaining constant. Or if we want to change the EI positions, okay, then it will be a horizontal curve. So, at any voltage, my current will remain constant. Okay. So, this is the representation of current source from the voltage source, and this is called as source transformation. Okay. Now, this source transformation will be used in many circuit reduction techniques. Okay. We need to reduce the circuit complexity. If I am interested in only one element, what is happening to that element with current, voltage, power, then the remaining circuit complexity can be reduced using source transformation, source shifting techniques. Okay. And I will be knowing what is the current or voltage at particular element. So, for this kind of analysis, we use source transformation and source shifting techniques. Okay. So, next what we would like to discuss is what happens when the voltage sources fall in series. It is not that always the voltage sources are single. There can be the combination of voltage sources that may come in series or in parallel. So, we will see what happens when the voltage sources are in series. Voltage sources in series. Now, let us consider first ideal sources. So, when two voltage sources, ideal voltage sources are in series, let this be the terminals A and B with voltage values E1 and E2. Now, the direction of both voltage sources are same. E1 is also in clockwise direction, the effect of E1 is also in clockwise direction, effect of E2 is also in clockwise direction. So, when the direction of voltage sources are same, the voltages add up. So, as a result of this, equivalently I can take a single voltage source of the same polarity as E1, E2, because both are in the same direction. So, I will be taking in the same direction with a voltage value of E such that E is equals to E1 added with E2, E1 added with E2. So, this is the equivalent voltage source when two voltage sources are connected. Now, suppose if both the voltage sources are in opposite direction, with voltage source E1 and voltage source E2. Now, direction of E1 is anti-clockwise, whereas direction of E2 is clockwise. Now, the effective voltage or the resultant voltage can be again represented with a single source with a voltage value of E, and this E is equals to E1 difference E2, E1 difference E2. So, if both voltages are in the same direction, I will add up. If both voltages are in the different direction, I subtract. Okay, I take the difference of 2. Then the resultant polarity of the voltage source is important. I cannot arbitrarily assign the polarity. Here the polarity issue is not existing because both voltage sources are in the same direction. Therefore, the resultant polarity will be the same as that of both the sources. But whereas in these two sources, the polarity depends upon which source is having the larger value. Suppose E1 is larger than E2, then the polarity of the resultant voltage source representation will be as that of E1. If E2 is larger than E1, then the polarity representation of the resultant voltage source will be as that of E2. Okay. So, let I take E1 greater than E2. So, with this, my polarity of the resultant voltage source will be following E1. If it is greater than E2 is greater than E1, then it follows the other way. Okay. So, this is what happens when the when the two voltage sources are falling in series. Now, these are the ideal sources. What with practical sources? Okay. So, two voltage sources, practical voltage sources, say E1 with internal resistance R1, E2 with internal resistance R2. Now the direction of E1, E2 are again same, both are in anti-clockwise direction. Therefore, the resultant is the addition equivalently. So the resultant polarity will be as that of the same E1 and E2 because they are same. So this E is equals to now E1 plus E2, and the resultant resistance R is the sum of two resistance R1 plus R2. So two resistors, internal resistors come in series with each other, therefore I add up. Now what if two polarities are different? So source value E1 with internal resistance R1, source value E2 with internal resistance R2. So equivalently I can write it as the source value of the resultant voltage source will be the difference. Again it depends, the polarity depends where depends upon whether E1 is larger or E2 is larger. So I will take one of the representation. Okay, so this is E equals to E1 minus E2 because I have assumed E1 to be greater than E2 here. With the polarity it is evident. Then the resultant resistance R, now R is again equals to R1 plus R2. One should not take the difference of two resistors. This is the common mistake done by the students which is observed. Because we are taking the difference of two source values of the voltages consciously or unconsciously, the two resistance values are also mistakenly taken to be the difference of two values. Okay, we should not do that. Whereas even though the two source values of voltages are the difference of two, the effective value is difference of two, the resistors internal resistance will add up. Okay, so this is common mistake what the students does in the exam. So this is what happens when the ideal voltage sources fall in series and practical voltage sources fall in series. So this is a common connection that we observe. The voltage sources may come in series. Now what if the voltage sources come in parallel? What should we do? Ideal sources in parallel. Ideal voltage sources in parallel. Now suppose I have two voltage sources of voltage values E1 and E2. So this type of connection is valid if and only if, okay, this is valid connection if and only if E1 is equals to E2. If E1 is not equals to E2, then this kind of connection is invalid. Invalid if E1 not equals to E2. Now why it becomes invalid? What happens if in practice I connect E1 and E2 with different values in parallel? Okay. Now with that, if I connect two ideal voltage sources in parallel of different values, there may be a circulating current flowing in the loop, and this circulating current may reduce the load handling capacity of the system, or it may cause a short circuit current of very large value in the loop, and which may also cause damage to the system itself. Now if I consider this loop itself, the resistance of the loop is 0, and suppose E1 and E2 are of different values, say the difference is large, suppose E1 is of 50 volts and say E2 is of say 500 volts, then there will be a circulating current, IC, whatever may be the direction, the circulating current IC, which is equals to 500 minus 50 divided by the loop resistance is 0. So this will result in a very large amount of current flowing in the sources, and if the source are not capable of handling this large current, they get damaged. Hence, we should always avoid in practice connecting two voltage sources in parallel if the voltage values of two sources are different. Okay, so that is considered to be an invalid connection. Still, if we go ahead with this kind of connection, then there can be a breakdown in the circuit observed. So this is about the voltage sources, connection of voltage sources in different combination in parallel as well as in series. So, in today's session we looked into how a practical voltage source and an ideal voltage source are represented, also how a practical and ideal current sources are represented, and how do we get a practical current source from the practical voltage source, and the various connection combinations of voltage sources in series as well as in parallel. Okay. So, with this we will end today's session. In the next session of electric circuit analysis, we will be looking into the practical connection and connection of the ideal and practical current sources, which connection is valid, which connection is invalid. So, with this we will end, and the next session we will continue with the connection of current sources. Thank you.